So question number one involves properties of exponents, and unfortunately there is no way around it. You either know these properties or you don't know these properties. And if you don't know these properties, then you couldn't do problems number one or two. To review, these are the typical properties of exponents that we utilize when we want to manipulate exponential expressions. We have the product property, which says if you multiply like bases, you can condense the exponential expression together by adding the exponents. We have the division or the quotient property, which says the exact opposite. If you divide like bases, you subtract the exponents. You have the power property, which says if you raise an exponent to another exponent, you can multiply those exponents together. Negative exponent property says that any base with a negative exponent forces you to take a reciprocal of the base. And lastly, anything to the zero power is 1. Now, when it comes to simplifying exponential expressions, there is no singular way to do it. There are lots of different pathways, different avenues to take. I'm just going to show one particular avenue. The first thing I notice is I see parentheses with an exponent on it, so that tells me to use the power property and distribute. Now, I'm going to take things slow and steady, one step at a time, so anything I do not highlight, I'm just going to copy down. So m negative 5, p to the negative 4, q to the negative 1, all over p to the negative 1, q to the 5, and this is the actual part I'm going to be doing math on, distributing the exponent of 3, that's p to the negative 6, q to the 9. Next, I notice that the denominator is quite noisy. There's a lot of stuff going on in the denominator. Notice how they're all multiplying each other, so it'll be an application of the product property. One thing to note about these properties of exponents is that they only work for like bases. In other words, don't mix up the letters. Just do the p's with the p's and the q's with the q's separately. Don't mix and match them. Again, anything I do not highlight, I'm just going to copy down for my next step. Negative 1 over. Product property says you add the exponents. So for the p's, it's going to be negative 1 plus negative 6 is negative 7. And for the q's, it's 5 plus 9 is 14. We have a whole bunch of negative exponents, so you could go ahead and use the negative exponent property. I think what I'm going to do is just go straight to the quotient property. I have a p on top, p on the bottom, q on top, q on the bottom. Now, if you look at the quotient property, it clearly says the exponent is a minus b, the numerator minus the denominator, and that's 100% a-okay. Instead, however, I like to do big minus small, and I just have to remember that if I do big minus small, my answer will be wherever the bigger number is. So let's set this equal. The m I'm not going to touch. Next, I have the p's there. Now, I got the two exponents, negative 4 and negative 7. Technically speaking, negative 4 has a bigger value. So I'm going to do negative 4 minus negative 7, which gives me a positive 3. And because negative 4, the bigger number, was in the numerator, I'm going to put my answer p to the positive 3 in the numerator. Working the q's, I have the exponents 14 and negative 1. Well, the number 14 is bigger than the number negative 1, so I'm going to do 14 minus a negative 1, which gives me a positive 15. And since the since the 14 was bigger on the bottom, I'm going to put my answer of q to the 15 on the bottom. The last thing that we have is the negative exponent rule, which simply says anything with the negative exponent, you're going to flip them. So I'm going to move the m to the denominator, giving me my final simplified expression of p cubed on top with m to the 5, q to the 15 in the denominator. Number 2 is the same concept. The only thing that's different is, well, we have fractions. And I hate to say it, but there's no running away from it. You need to be comfortable with fractions, or at the very least, you need to be comfortable about using a calculator to handle these fractions. But the simplification, the properties, all the same. First thing I notice is a parentheses with an exponent, so I'll go ahead and use the power property and distribute that exponent in. So that's x to the 7 halves, y to the negative, what's that? Cancel out, so that's a 7 over 6. And then everything else just copy down to thirds, x to the 1/2, y to the negative 2/3, z to the 1/2. I see multiplication happening in the numerator, so I'll use the product property to combine these guys. So that gives me x to the 7/2, y, and then all I need to do is negative 7/6 plus 2/3, which is negative 7/6 plus 4/6, sorry. That gives me negative 3/6, which I suppose you can reduce to negative 1/2, right? So this is y to the negative 1/2 over x to the 1/2, y to the negative 2/3, z to the 1/2. Then we have quotient rule. So we have these x's here and these y's here. Unfortunately, that z does nothing. It just stays put. And so then the rule goes, we subtract, and I like to do big minus small. So for the x's, you do 7/2 minus 1/2, which is 6/2, which is 3. So you get, and the 7/2 is on top, so you have x cubed on the top there. For the y's, technically negative 1/2 is bigger than negative 2/3, so we'll go ahead and do negative 1/2 minus negative 2/3. So that's going to be negative 1/2 plus 2/3. Common denominator is 6. That's negative 3/6 plus 4/6, which is 1/6. And again, since the y's are big and on top, I'll put my answer of y to the 1/6 on top and the z to the 1/2 on the bottom. Technically speaking, we have fractional exponents in the denominator. We should rationalize, but I didn't say you had to rationalize for this problem, so this was all I was looking for. I do ask you to rationalize for problems 3, 4, and 5, however. And the idea of rationalization is to get rid, in this instance, to get rid of the radical. Now, which radical do we get rid of? The instructions explicitly say rationalize the denominator. Now, the only concept that we need to know is that we have to know opposites. We have to know that the opposite of a square root is something squared. The opposite of a cube root is something cubed. The opposite of a fourth root is something to the 4th power, so on and so forth. So in this instance, to rationalize means to get rid of the square root of 2. To get rid of a square root, well, the opposite of a square root is an exponent of 2, a square. And squaring literally means multiply by itself. So, to rationalize this guy, I'm going to multiply by radical 2. But of course, what you do to the denominator, you have to do to the numerator as well. So if we go ahead and distribute that radical 2 in the numerator, we get 9 radical 20 plus 8 radical 2 over. Now in the denominator, the whole point of rationalizing is to get rid of the radical. So radical 2 times radical 2, just by design, by construction, it's just a regular 2. When you multiply square root by itself, you get rid of the square root. So in the denominator, we have 7 times 2, which is 14. Now, the instruction did say simplify, and I know that square root of 20 is pretty big. We can probably simplify him. That's the same thing as square root of 4 times 5, which, of course, square root of 4 is 2. So note that the 2 radical 5 is just the square root of 20. Well, we have a 9 in front of it. So when we simplify square root of 20 as 2 radical 5, we have to multiply the 19, which gives us 18 radical 5s. Plus 8 radical 2 over 14. Second, when we simplify fractions with lots of pieces, we have multiple terms in the numerator and radical terms, you have to look at every single coefficient. In other words, we have to look at every single outside number. A fraction is simplifiable if every single outside number can be reduced at the same time. So you have to ask yourself, is there a common number that can divide out from all 3 numbers rather than 2? And in this instance, the answer is yes, we can divide out a 2. So the most simplified answer would be 9 square roots of 5 plus 4 square roots of 2 all over 7. Number 4 is the same concept, except we're dealing with a cube root instead of a square root, but the idea is still the same. We want to get rid of a cube root. What do we need? we need a perfect cube. So notice what we currently have inside the radical, just a 5. So the idea is this: we have a 5, and we want a perfect cube, 5 cubed, which, if you forgot, simply means multiply by itself 3 times. So this is not a trick question. We have a single 5. I hope everyone can see that we need a 5 times 5, which is another way of saying 5 squared. So that's what we're going to do. We're going to multiply by 5 squared, but since it's a cube root, we need to put that 5 squared inside of a cube root. And of course, what you do to the denominator, you got to do to the numerator. Okay. So multiply straight across gives us 25 cube roots of 5 squared, which is also 25, all over. And again, the whole point of doing this part is that it gives us 5 cube inside of a cube root, which is just a simple 5. Now when it comes to simplification, we look at the outside numbers, and of course 25 and 5 can reduce, giving us a final simplified answer of 5 cube roots of 25. Number 5 was rationalizing when there's a square root in a binomial. So in this example, we need to individually square the terms. Now, there's only one math way I know of that can individually square terms, and that's to exploit this pattern here. The product of two conjugates will give you the difference of the perfect squares. Notice that the individual terms are being squared. I saw some people try to do this. Oh, I'm just going to square it. And they did this. Oh, that's just, 2 plus 49. That is wrong. When you square a binomial, it doesn't distribute. The properties of exponents don't apply because of that pesky plus or minus. Recall that if you square a binomial, you get this pattern here. You get this extra middle term, which is annoying to us if we want to rationalize. So we want to avoid this pattern and instead use the above pattern. So the technique is to multiply by the conjugate, radical 2 minus 7, radical 2 minus 7, and then just go ahead and distribute across. So that gives you 6 radical 2s minus 42 all over. I mean, I guess technically you could FOIL out the denominators, but remember, it's just following this pattern here. So you know it's just going to be the first guy squared minus the second guy squared. So the first term, radical 2 squared, is just a regular 2 minus the second term, 7 squared, which is 49. And then you just go ahead and simplify. Okay. Again, when it comes to simplification, you ask yourself, is there anything I can reduce from the regular numbers? The answer to that in this case is no. So this is as simplified as possible. I would have totally accepted this answer. Some people don't like the negative to be in the denominator, so they inject the negative to the numerator. So if you were to use the negative in the numerator, it would have gotten you this answer. Both are 100% the same. I would have accepted either. Six is a factoring quadratics problem, and I hate to say it, but factoring quadratics, it's not a thing you can figure out or calculate. It's not an algorithm. It's just one of those things where you know how to do it or you don't know how to do it. It's 100% pure logic. So if we don't have factoring down by now at this stage, we are far, far behind and we need to play catch up. But this is my thought process, at least. If I was to factorize a quadratic trinomial, I know it would be a product of two binomials. The logic is whatever you put in this position has to multiply to the first term. Now we have k squared here, so that is sort of nice because we only have one choice, k times k. That's the only nice things that multiply together to give us k squared. Whatever you put in this position has to multiply to the last term. To figure out the possibilities, I like to do what is known as pairwise factor. Find all the pairs of numbers that multiply to whatever number you're breaking down. Now, I do this systematically. I always start with 1 in the number, and then from 1 move up to 2. And I ask myself, does 2 divide into 90? In this case, the answer is yes, 45. And then just keep incrementing it by 1 until you complete the list. Does 3 go into 90? Yes, 3 and 30. Does 4 go into 90? No, skip it. Does 5? Yes, 5 and 18. No, that's not right. Yeah, 18. Yeah, that's right. Does 6 go into it? Yes, 6 and 15. Does 7 go into it? No. Does 8 go into it? No. Does 9 go into it? Yes, 9 and 10. The next number I would test would be 10, but since I've already written him down, I know I've completed my list. You know you're done when you go full circle in the list. Next thing I do is I look at the last symbol here. It's a plus sign, so that tells me to think of add. So now this is my thought process. What pair of numbers above adds to the middle number of, in this case, the middle number is 19. And hopefully it's not a hard thing to do. You just go straight across and see which one adds to 19, which obvious statement is 9 and 10. So the last thing we need to do is figure out the pluses and minuses, and I suppose this is where the guess and check comes into play. How do I know if it's positive or negative? What I do is I write down the two numbers that are blank and set it equal to the middle number, including the sign. So including the sign is a plus 19. So your job is to figure out the pluses or minuses on these numbers to make this a true statement. What 9 plus what 10 gives you a positive 19? And I hope it doesn't take a lot of thinking to know that positive 9 plus positive 10 will give you positive 19. So there is our factored form. Number 7 is the same idea of factoring. The only thing that's different is that the leading coefficient is not 1. It's similar to thought processes, just with some minor tweaks. So if he's factorable, he's still going to be product of two binomials. Whatever I put in the first position still multiplies to the first term here. The only difference is it's not just a 1m squared, it's a 7m squared. Fortunately, 7 is prime, so there's only one choice, 7m times m. We don't have any other choices of natural numbers that multiplies to 7. And then whatever I put in the last position still has to multiply to the last number here. So you go ahead and pairwise factor him, 1 and 8, 2 and 4. And the last symbol makes you think of subtraction. However, because this number here is 7, you should know that when you FOIL out, that whatever number you put into here will eventually be multiplied by 7. I guess I shouldn't write that. I should write it down here. Whatever you put into here will be times by 7. So it changes your logic a little bit. This is the logic you should be thinking of. What pair of numbers such that, ST is such that when I multiply one of them by 7 and then subtract gives me, and the middle number in this case, I don't see any, so it's a 1. And I don't know what the answer is. I haven't done this before, so I'm literally just going to guess and check. So yes, this is where it takes trial and error. You're going to have to put some work into it. So I'm just going to start randomly at the top here. And let's just multiply the 1 by 7 and ask yourself, 1 times 7 is 7 minus the 8. Hey, I got lucky. That gives me a 1. So in this case, I got it on the first guess. But I've had problems where I got it on the 5th guess, on the 3rd guess, on the 7th guess. You just got to keep trying until you get it right. So notice it was 1 times 7. So that means I need to put the 1, I must put it here, and the 8 here. So now I'm going to figure out the symbols, the signs, the pluses and minuses. So what you do is you put the numbers down. So I'm playing with the 8, and technically I'm playing with the 1, but it's 1 times 7, which is 7. And I want to equal the middle number with this symbol. So that's a negative 1. Play with the pluses and minuses. It's a puzzle, figure it out. Hopefully it doesn't take us long to realize that negative 8 plus a 7 gives us a negative 1. So the 8 needs to be negative, and the 7, which came from the 1, is positive. Now let me just rewrite it all nice and clean. So all this work tells us that the original quadratic factorizes into 7m minus 8 times m plus 1. That is the factored form. Number 8, more factoring, same idea. The only difference is, again, the leading coefficient is not 1. But notice that the leading coefficient is 6. Now, 6 is a number that has multiple possibilities. It could be 1 and 6, 2 and 3. So the only different thing about this example is that you got two possibilities. It could be 6x and 1x, or 2x and 3x. And the last number is a 10, so you pairwise factor 10, 1 and 10, 2 and 5. So you got more guesswork, and that's all it is. Factoring quadratics isn't anything special or crazy different. It's just you got to put some work into it. So I'm not going to explain this problem. It's the same logic as the previous two. So if you factored correctly, if you did the work to guess, you'll find out that it's not 2x and 3x. It's actually 6x and 1x. More specifically, 6x plus 1 and x minus 10. That's the factored form for number 8. Number 9, more factoring, but it's an a to the 4th power. The idea for this question was to test you whether or not you recognize the pattern. The first exponent is exactly twice as much as the middle, and it ends in a constant. That is classic quadratic form. To make it look like a quadratic, we're going to use a variable substitution. So we're going to let the letter u, or whatever letter you want, equal the middle variable part, in this case a squared. That transforms our problem into u squared plus 10u's plus 21, which is a regular quadratic, hopefully, that you can easily factor now. That should be u plus 7, u plus 3. Now, the original problem wasn't in terms of u, it was in terms of a. So make sure if you use variable substitution, once you get your final factor form, to resubstitute the original equation, original variable in. So wherever you see a u, change it to an a squared. A squared. This is the factored form of the original problem. Number 10, if I ever ask you to factorize 4 terms, it usually means the technique is factor by grouping. To do factor by grouping, you split the problem in half. Look at the first 2 as its own piece, and then you look at the last 2 as its own piece. And do notice how I sort of highlighted the symbol in the second piece. You always want to include whatever that symbol is. So if I were to rewrite this problem, it would be 8b cubed plus 28b squared in its own parentheses, always a plus, and in the second parentheses include the sign in front of the term, plus 14b squared plus 49. So just to reiterate, you always put a plus sign here, and this plus sign, or this symbol, is dependent on whatever the original symbol is. And then once you separate it into 2 smaller pieces, the name of the game is GCF, factor out the greatest common factor. So from the first set, I can factor out a 4b squared, leaving behind a 2b plus 7. And in the second set, I can factor out just a 7, it looks like, leaving behind a 2b plus 7. Notice that these 2 parentheses are the same. That's what we want. Because they're the same, that means we can factor out the 2b plus 7. And in normal factoring, whatever you factor out, you always have a second parentheses for your leftovers. And hopefully you can see that we have 4b squared plus 7 as leftovers. This is the factored form. Oops. Looks like I double pasted number 10 here. Number 11 was a multiplying rational expressions problem. Now, as I said in class, when it comes to multiplying or dividing rational expressions, it's sort of ironic. You don't do any multiplying or dividing. The name of the game when it comes to rational expressions is factoring and canceling. So if I ever ask you to multiply, divide rational expressions, I don't expect you to multiply, divide, just factor. Now, one thing I did not notice from this problem was computer made, was that it actually gave us like it did half the work for us. If you notice, before I do any factoring, this numerator is 100% the same as this denominator. So he immediately, without doing any work, crosses out. I didn't expect that to happen. I didn't want that to happen, but hey, you lucked out. That means all I have left over is this numerator here and this denominator. And guess what? The numerator is polynomial. The denominator is just a number. Nothing will cancel out. So believe it or not, you have nothing to do. This is n squared plus 3n minus 4 over 5. That's the answer. I suppose if you felt like it, you could factor n plus 4, n minus 1 over 5. But yeah, this was sort of an easy problem. I guess you got a freebie on the quiz. And taking a look at this one, this looks like another freebie question. So this is a division problem, but all division problems are the same thing as multiplication problems once you change division to multiplication and take the reciprocal of the divisor. So this equals, first fraction stay the same, 2b squared plus 11b plus 15. Change the division to multiplication and then reciprocate the divisor, the second fraction. And darn these computer-generated problems, you got a freebie here because these guys immediately cancel out. But you still have to factorize these pieces because they don't cancel out automatically. So the yellows got canceled out to ones. The reddish-orange factorizes into two parentheses, 2b and b. What is this going to be? 5 and 3. So that's 6 and 5. So plus 3 here, plus 5 there. That would work. And then the light bluish, since it's a binomial, the only thing you do is GCF. So you can factor out a 2b squared, leaving behind a 2b plus 5. And then the yellows factor out to 1. Do some cancelization. The 2b plus 5 cancels out. And that's it. That's all you can do. So what's left over on top is 2b squared. What's left over on the bottom is b plus 3. That is the simplified form. Number 13 is a compound or complex fraction problem. Lots of different techniques to simplify this. The technique I like is clearing the fraction. And to clear the fraction, we need to find the LCD. Now, if you can't know what the LCD is by just looking at it, what you have to do systematically is to look at the inner denominators, what I'm highlighting, and go ahead and write them out vertically, stack them together on top of each other. So we have a denominator of x minus 3, denominator of 12, denominator 4, denominator 4. And what you want to do is factorize everything if possible. I can't do anything with the x minus 3, so it stays put as x minus 3. Notice how I put them in parentheses because they belong to each other. You can't split them apart. 12, if you prime factorize him, with the factor tree and all, you get 2 times 2 times 3. 4 is 2 times 2. 4 is 2 times 2. So the LCD, what you want to start with is look vertically, up and down, not left to right, and you look for common factors. Hopefully this is very obvious now that everything's broken apart. You have a 2 in common. You have another 2 in common. And that's it. I do not have 3's in common because this top 3 is attached to the x. So that's all what's in common. So what's left over once you write down everything that's in common are all the factors that are not used. I did not use this 3. I did not use this x minus 3. So the LCD is 2 times 2 times 3, which is 12 x minus 3's. Next, what I'm going to do is rewrite the problem, but with some spacing, because the technique of clearing a fraction involves multiplying everything by the LCD. So to rewrite the problem, we have 4 over x minus 3, leave a gap, plus x minus 3 over 12, all over x minus 3 over 4, leave a gap, minus 3 over 4. Then just multiply everything by the LCD. 12x minus 3, 12x minus 3, 12x minus 3, 12x minus 3. If you played your cards right, the fact that we use an LCD means all the denominators should cancel out. So in the top left corner, x minus 3's will cancel. Top right, 12's will cancel. Bottom left, the 12 and the 4 will reduce. So the 4 goes away and the 12 becomes a 3. And then the bottom right, same thing. The 4 and the 12 will reduce. So all that's left to do is multiply the leftovers. So on the top left, we have 4 and 12, which makes 48. Plus, in the top right, we have x minus 3 with x minus 3. So, on the side of scratch work, if you need to, x minus 3, FOIL them out. That's going to give you x squared minus 6x plus 9. Over in the bottom left, we have x minus 3 times 3. Oh, you can't see that. 3. X minus 3 times 3 and x minus 3. So I already know what x minus 3 times x minus 3 is because we did it over here. So all I know is it has an extra 3. So it's going to be a 3x squared minus 18x plus 9 minus hold on a second. Did I do something? No, that's right. Minus, then here we have 3 times x minus 3, which is just 9 times x minus 3. But do be careful. It is a subtraction problem, so you have to include that negative as well. So when you include the negative, you get negative 9x plus 27. So it's negative 9x plus 27. All that's left to do is combine like terms and simplify if possible. So in the numerator, I just have 48 and 9 as like terms. In the denominator, we have negative 18x with the negative 9x and the positive 9 with the positive 27. So in the numerator, this equals x squared minus 6x plus 57. And then in the denominator, we have 3x squares minus 27x's plus 36. Try and factor as, oh, no, actually, sorry, my mistake, haha. This shouldn't be a 9. This should be a 9 times 3, which is a 27. So you have 27 plus 27, which is a 54. That should be the correct answer. Yep. Number 14 is just, it looks like a complicated linear equation, but it's a linear equation nonetheless. There are no x squares, x cubed, and so forth. So like all problems, there are multiple ways to do this. I'm only going to show one particular pathway. I like to break down parentheses as much as possible. That usually means distribution. So go ahead and distribute these guys out. And that gives you a negative 3x plus 18 minus 30 minus 5x equals 2 minus 8x plus 7x. Next, I like to combine like terms. So on the left-hand side, we have negative 3x with negative 5x as like terms, 18 with a negative 30 as like terms, and on the right-hand side, we have a negative 8x with a 7x as like terms. So combining the yellows gives us negative 8x, combining the blues gives us negative, 12? Equals 2's by itself, and combining the reddish orange gives us a negative x. Solving equations 101, get all the variables on one side, get all the regular numbers on the other. Hopefully we can do two steps at once. Let's add the 8x over, and at the same time let's subtract the 2's. So these guys are gone. That's negative 14 equals these guys are gone. That's a 7x. Divide both sides by 7. Get x equals negative 2. Number 15 is also a linear equation, but it has a special symbol and an absolute value symbol. So the general rule when you have absolute values in an equation is before you can actually solve it, you want to get the absolute value by itself. So notice by highlighting the absolute value, it makes it clear, I hope, that we need to get rid of this 9 and we need to get rid of this negative 10 here. And to solve an equation, you always get rid of the thing that's farthest away first. So we're going to get rid of that positive 9 by subtracting. Negative 10, absolute value 2 minus 2b equals negative 40. And then to get rid of that 10, I'm going to divide out the negative 10. So we get absolute value 2 minus 2b equals 4. Now, how do we handle absolute values? Well, we have to recall the definition. Recall that absolute value of anything, absolute value of x, will always spit out one out of two things. It'll always give you the exact same thing you put into it, or it'll give you the exact opposite. When does it do what? Well, it gives you the exact same thing right back out if what you put into it was not negative. But if you put a negative number inside of an absolute value, you get the exact opposite out. How does that help us? Which variation of the definition do we use? Well, in our equation here, since what's inside of the absolute value contains a variable, and we don't know what that variable is, we can't definitively say if it's absolutely positive or negative. So as mathematicians, we sort of have to hedge our bets. We have to consider both cases. So by definition, this absolute value could give me the exact same thing right back out, then 2 minus 2b. But according to the equation, he equals 4. Or by definition, this absolute value could give me the exact opposite. And to do the exact opposite, you just surround it by parentheses and slap on a negative, which equals 4 at the same time. Now you have two linear equations that I hope we can solve sort of automatically. Let's work on the left side first. Subtracting the 2, negative 2b equals 2. Divide out the negative 2, you get b equals negative 1. Let's work the right equation. You can go ahead and distribute that negative if you want. I like to divide out the negative. That's only because then to solve it, use the same steps as the left equation. So that's 2 minus 2b equals negative 4. Subtract the 2, you get negative 2b equals negative 6. Divide out the negative 2, b equals positive 3. Now let's take a look at the equation when the absolute value is by itself, this step here. Now, as good mathematicians, we technically should always be checking our answer, but if your absolute value equation just equals a simple number, if you trust your math, trust your arithmetic, whatever answer you get is usually going to be the answers. You really don't need to check your answer until or unless you have variables on both sides. Number 16 was just a simple quadratic equation. I think I gave you a hint on the quiz. I told you explicitly it was factorable, asked you to solve it by factoring, but honestly, if you solved it by quadratic formula completing the square, I would have been happy. The idea to solve a quadratic is you want 0 on one side, so hopefully we can do two steps at once. Let's subtract the v squared over, and let's subtract the 8v over. That gives us this equation here, 7v squared plus 52v minus 32 equals 0, and then you just go ahead and solve it by factoring, quadratic formula, completing the square. Numbers are pretty big, but it should be factorable because I told you it was factorable. 7v and v. The last number is 32, so that's 1 and 32, 2 and 16, 4 and 8, 5 doesn't, 6 doesn't, 7. Okay, so that's it. The last symbol's a minus, so I'm going to think of subtract and times 7 for one of them. So let's just guess and check. Let's guess the top one. So I'm going to multiply the first one by 7. It gives me 7. Minus 32 is not 52. And I'm not going to even bother 7 times 32 because that's way too big. So it's not the first row. Let's try the second row. 7 times 2 is 14. Minus 16 is not big enough. 7 times 16 is like, I don't know, really, really big. It's not going to be that either. So let's try the third row. 7 times 4 is 28. Minus 8 is not enough. So let's try 7 times 8 is 56. Minus 4 gives me the 52. So I know it's 7 times 8. That means the 8 needs to go here in order to get times by 7. And the 4 needs to go here. So the numbers I'm playing with are 4 and 56. And I want it to be a positive 52 in the middle. Hopefully it's very easy for everyone to see that the symbols should be negative 4 and plus 56. Or in other words, negative 4 here and plus 8 there. Now the reason why we want 0 on one side and factorize it is because we can use the zero product property now. Zero product property states if you have a multiplication problem, which we do here, and equals 0, which we do there, you can go ahead and set each factor separately equal to 0, and then solve. So add 4 to the left side here, divide out the 7, and for the right equation, you can go ahead and subtract 8. V equals -8. So those are the two answers, -8 and +4/7. Number 17 is a rational equation, a fractional equation that looks difficult, but the name of the game is just clearing the fraction, just like what we did for simplifying compound fractions. So again, if you can't tell what the LCD is by just looking at it, there is a method. Go ahead and write down the denominators. Factor if you can. I can't here. I can't here. And I can factor out an A. Hopefully it's very obvious to see that the LCD, you have an A plus 6 in common. With the leftover A, it's just A times A plus 6. Then you want to go ahead and rewrite the problem with some spacing. So, here we go. So we have 1 over A plus 6, leave some space, plus A minus 1 over A plus 6, leave some space, equals A plus 2 over, and I'm going to go ahead and write the denominator in factored form. Then multiply every single term by the LCD, A plus 6, A plus 6, A plus 6, and then all of the denominators should cancel out. A plus 6's are gone, A plus 6's are gone, both the A's and A plus 6's are gone. So all that's left to do is just multiply the leftovers. So all that's left here is 1 times A, which is just A, plus A minus 1 times A, which is A squared minus A, equals A plus 2 is the only thing that's left over. Notice it's just a regular quadratic, so bring everything onto one side. Well, actually, let's combine like terms first. We got a minus A and a plus A, so those guys are gone. And then I hope it's not hard to see that you subtract the A and subtract the 2 to give you A squared minus A minus 2 equals 0. Solve it by factoring, completing the square, quadratic formula, what have you. Ends up being this guy's factorable. A minus 2, A plus 1 equals 0. Which hopefully you can see gives you A equals 2, A equals -1. Now, when it comes to rational equations, you really don't have a choice. You must check your answers. And you really only need to check it against the denominators. So the denominators that we were working with were A plus 6's, A plus 6, and A plus 6. If at any moment your potential answers here, A equals 2 and A equals -1, makes any of these factors equal to 0, you have to throw them away. But notice if you plug in an A equals 2 or A equals -1, none of those guys will equal 0, so we're safe, we're good. Both of these guys are good answers. Last but not least, number 18. It's a radical equation, and just like with absolute values, this is sort of a special symbol. You don't want to start solving until that symbol is by itself, so hope you can see that that means we got to get rid of that 1 there. So to get rid of a positive 1, you go ahead and subtract 1 from both sides. Gives us radical 3r plus 7 equals r minus 1. And then we can, now that the radical is by itself, square both sides. Right? Please, 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 I saw a lot of people make this mistake. When you square both sides, you cannot distribute the exponent because of that minus sign. You have to write it out twice, or simply know the pattern, r squared minus 2r plus 1. Right? So that's what the right-hand side will be. So back to our problem, the square root and the square cancels, giving us 3r plus 7. And the right-hand side is an r squared minus 2r plus 1. Notice it's a regular quadratic, yada, yada, yada. We've done this a bajillion times now. Get everything onto one side. I'm going to subtract the 3r, subtract the 7, giving you 0 equals r squared minus 5r minus 6. Solve it by factoring, quadratic formula, completing the square, whatever you want. Ends up this guy is factorable. R minus 6, r positive 1. giving us r equals 6 and r equals -1. Now, if you look at the equation before we squared both sides, right here, notice we have variables on both sides. We have r's on the left and the right. So that is a signal that we must check our answers. And when you check your answers, you check it into the equation before you square both sides. So I'm going to check it into the 3r plus 7 equals r minus 1 form. You cannot check it after the square both side steps. So to check, just plug it in. 3 times 6 plus 7 equals 6 minus 1. That is 18 plus 7 is 25 equals 5. And of course, 5 does equal 5. So r equals 6 is good. Let's check r equals -1. So we get the square roots of 3 times -1 plus 7 equals -1 minus 1. So that is -3 plus 7 is 4, it's -2. And 2 does not equal -2. So this is a bad answer. We have to throw them away. This problem only has one answer, r equals 6.